Okay, so let's start with the rest of the schedule for the workshop. So our next talk is from Google on P4-based automated reasoning for the networking masses. Over to you.
That's right. So to quickly introduce myself, I'm Steffen. I lead a team called the P4 team at Google. And so this seemed like a great occasion to talk about what it is that our team does. And so first of all, I want to acknowledge this is really the work of a lot of people, the whole P4 team, many of who are here. Some of my predecessors, Konstantin was here earlier. I think he went to the restroom. Several interns who are also here, some of which are here. And so really a large body of work over the last 5+ years. So with that, let me jump in. So the way we use P4 at Google is a bit unusual. P4 was designed initially to be a programming language for P4 programmable ASICs, such as the Tofino chip. But at Google, we have a lot larger variety of networking ASICs, and not all of them are fully P4 programmable. And yet, we find that P4 is really, really useful for us. And let me show you why. So we view P4 as a specification language. And so we write P4 programs as these machine-readable specifications that capture all our requirements for a switch in a specific deployment role. And so we have a number of these for different switch deployment roles. And so let me explain a bit better what I mean by capturing all the requirements. So let's take a middle block in a data center. Here's the P4 program, or a small caricature of what it might look like. And let me show you in what sense it tells you about the requirements for this role. So the first aspect is that it kind of defines all the objects on the switch that you can program. So it defines the control plane API of the switch, or the schema. Tells you what kind of table entries you can install, modify, delete. And the second thing it tells you is precisely how a switch with a given set of table entries should behave. What is the data plane behavior, right? How should it forward packets? And it tells you that in a machine-readable and unambiguous way. So a very precise specification of what it is that we want from the switch. And let me explain a bit why we think this is very, very useful, how we use it. So at Google, we use software-defined networking. And let me talk specifically about the data center here. So in the data center, we have our SDN controller. And if you think about something like a data center middle block, that is actually the kind of requirements that an SDN controller has are actually pretty moderate. Basically, you need to do L3 forwarding and WCMP. That's pretty much all we need for our data center switches. So very moderate set of requirements. But if you contrast that to what you get from a typical network ASIC, that is kind of this extremely powerful machine, amazingly machine, but there's some downsides to that power, right? So it has this ginormous space of possible configuration knobs, and that makes it somewhat unpredictable because no one has explored this entire space of configuration knobs, right? Like a simple counting argument shows you that no one could have possibly explored this space. And so sometimes we find surprises there, right? And so how do we kind of address this discrepancy between our requirements, which are pretty moderate, pretty small, and this enormously powerful machine that's kind of complex and sometimes unpredictable? Well, the first step is we turn our requirements into a P4 program, as I had mentioned. And then we use that P4 program to essentially restrict the view of the SDN controller to the switch. So the SDN controller sees this complex machine through the lens of the P4 program. And as such, what it sees is actually a kind of an embarrassingly simple API. Certainly for a middle block switch, it's kind of embarrassingly simple. And the benefit is, what do you get in return? Well, this machine actually becomes now very, very predictable. And we have put a lot of effort into making it so that is extremely predictable. And that's what P4-based automated reasoning is. And I'll tell you in a second how it works. But before I get there, I just want to mention in passing, there's some additional benefits beyond just making our networks more reliable. Oh, and yes, this makes the switch appear like a beautiful beast to the SDN controller. But there's a few more benefits here. So it's not just about reliability. It also allows us to move much faster. We can introduce new features much quicker to the network because we're much more confident that they'll work correctly. And there's also a nice benefit of optionality. Because our set of requirements is very, very clearly defined, and the complexity of the machine is sort of abstracted, we can swap in different generations of ASICs into the same deployment role and be confident that the network will still work just as before. So we'll refer to that as optionality. But for now, our main focus will be on reliability and P4-based automated reasoning, so the way we achieve that. So here's a 10,000-foot view of P4-based automated reasoning. The high-level idea is very simple. You start from your P4 specification, and then we have all these fancy tools, which I'll abstract for a second. But what they do is they take in the P4 program and they output a test. And a test is essentially a switch input that gets fed to your switch under test and an expected output. And what you do is you run the switch under test, it produces some actual output, and you have your expected output, and you compare the two and make sure that they match. And all of this is fully automated. That's kind of the key, right? So you write your P4 program, but after that, you get all the testing for free, and you can make sure that your switch under test behaves precisely like you specified in your P4 program. So we will actually have a talk after this that talks about one of these tools in more detail, and Jonathan will also tell us a bit more right now. And maybe you have heard about P4 Test Gen. That is actually one of those tools, although not developed by us, but by Fabian. But we have similar tools in-house. And so this has been very successful at Google. It has been used for every data center deployment role since 2020. Found many, many bugs. We have missed almost no bugs. And we've published this work as well. And you can see here a graph that these are relevant bugs that get quickly resolved. So let's talk about the problem. So far, I've talked to you how things work well, but there's also some problems. The main problem that I want to talk about today is scaling this to the masses. So since this has been successful, the demand on our team has increased substantially, as you can see from this graph. So we started with a very simple role, middle block, moved on to another role, fabric border. Recently, we have had 2 more roles, and it just keeps going. However, we didn't really build our tools with this in mind originally, because our main focus was to prove that this approach works in the first place. And so we're running into some challenges there. And our team size has been pretty much constant ever since then. So how do we deal with this? So let's take a closer look at why is this a problem and where do we spend our time? So if you look at the cost of this automated validation with P4-based automated reasoning, there's the first part, which is we need to develop the tools. And this is this is where we want to spend our energy, right? And they're general purpose tools, so they actually work for any P4 program. So that part is great. But there is some cost that you pay for every single P4 program. And that is less good, right? Because as we've seen, the number of programs is increasing. One is the instantiation cost. Like, our tools don't magically just work for a new program. You kind of need to set them up. So that's the first part. And once you've instantiated your tools, well, they do what they were designed to do. They find a lot of bugs. And once you have found those bugs, someone has to look at them and actually find out what is even wrong here. And so that there's some cost here that scales with the number of bugs you find, which is the root causing cost. And traditionally, we have paid all of those costs. Our team has paid all of them. And that clearly doesn't work if the number of programs keeps increasing and the team size is constant. The other problem that I will be happy to admit is that we were not aware of this formula. So naturally, what did we do? We invested in finding more and more bugs, right? That's the obvious thing to do for someone who works on problem methods. Let's improve our tools. Let's find even more bugs. So that makes matters worse. But now that we're aware of this formula, we have sort of changed course for some time. There's some obvious ideas here. Obviously, you want to bring down these costs that scale with the number of programs, so the cost of instantiation and root causing. And we can do that through automating root causing and building better APIs that are easier to instantiate. But there's actually a third idea that I would say is maybe the most important idea. And that is to empower the users of P4-Bar to do a lot of the work themselves. So instead of just bringing down the costs, that is not really enough if the number of programs, keeps going up and up and up. Let's have the people who run those programs, who are bringing them to production, help. And actually, they really appreciate that, right? If they can do the work, and it's easy for them, then they love to do that. And so that is actually kind of the most important part. And that allows us to focus on building the infrastructure. And so this has really been our mission for now, I would say, probably around 2 years, transitioning to this infrastructure provider role. And at this point, I'll hand it over to Jonathan, who will tell us about the details of how we went about this.
Thank you, Steffen. I'm Jonathan. I'm also on Steffen's team. And I will tell you about, I'm going to concretize these ideas for you. So number one, I want to tell you about our first approach to kind of these two ideas, idea 2 and idea 3, which is all about building high-level APIs that could be used by our clients. So to look at this, let's think about an example of how we actually use this. And this is one of our prime use cases. We use this for data plane validation, like we've already said. And historically, the way that this looked was we had this fairly simple looking workflow where we started with production entries from some program in the sense that he described previously. And then we had 2 tools that we sort of mainly use, this P4-Symbolic, which is what Meghana and Ollie will be talking about in the next talk, which generates input packets that try to hit all of the production entries, more or less. And then we have the P4 simulator and the actual switch. We run the input packets through both, and we verify that they match, much like what Steffen was saying before, right? Okay, and this looks like a very, very simple picture. This is a picture that you may have actually seen before if you've ever heard any talk by us in the last 4 years, roughly. But actually, we simplified this 4 years ago a lot for the talk. These modules were not quite so modular as they looked. This was a sort of complex weave of interdependencies, I would say. And therefore, once we started having a second program, as Steffen was talking about, suddenly we needed to weave that into these modules that we had. So our first part idea wasn't very interesting. It's exactly what Steffen said, right? Just make modular APIs. So we spent a lot of engineering effort, but not a ton of ingenuity necessarily, to actually modularize these, make them very nice and reusable. But actually, we don't want our clients to have to think about the details of how any of this works. We think it would be even nicer if they just had one single big high-level API that they could say, hey, just tell me if my switch is working correctly. It would be amazing if they could just make this single function call, more or less. And so we thought very hard about what is kind of the minimal amount of information that our client can give us so that we can do something very useful for them. And one thing we definitely need is the switch under test. If we don't have a switch under test, there's very little we can do. And so now we thought about what can we actually get just from having the switch under test? Well, it turns out more than you might imagine. From the switch under test, we can read back the P4 specification that is used to configure it and the table entries that are on it. From those, we can pass this into the P4 simulator, and this kind of gives us all of the state that it needs to accurately tell us what's going to happen if some packet comes in there. We can send the same things to P4-Symbolic, which can generate a bunch of packets that try to hit these table entries that are on there. And finally, we can do this verification. And so what this means is that now the only thing that a client needs to give us, which was a configured switch, more or less, right? They need to set it up with a P4 specification. They need to install some table entries that they think are interesting. And then we can tell them that the data plane that is, the possible data plane behaviors that now exist on this switch are correct, more or less. So just to hammer home this ease of use a little bit, basically we created a single function that we call divas. I think I had that as the title, but I didn't say it. Data validation as a service. They pass in their test bed, more or less a switch under test, plus some crux. We say, is this okay, yes or no? we can give them more information. We'll get to that in a moment. And as a quick example of where we use this now in our real, in Google, in the real world, is we have this replay testing where we just configure the test bed first, we replay our production snapshot, and then we run debus. And now it tells us, does this production snapshot, which we can update however often we want, work correctly? And that's been a very, very powerful protocol. And again, just to really hammer home how easy this is the entirety of the code that it takes to use this tool. Fits on this slide. You can even read it from back there, probably. Thank you, Fabian. I appreciate the fake applause. All right.
Gotten a lot simpler.
It has. Yes. Constantine's knows how bad life was, how amazing life was. Heroic effort at leading us to the place we wanted to get. Okay. So with that, we have this very simple API. We've reduced some of the costs that Steffen talked about before, right? The cost of instantiation in particular, and we've made it possible for a client to take on some of these costs for us as part of their individual program, which they're interested in leading, right? And that means that now we could shift some of our resources to the thing we really wanted to do, as Steffen mentioned, this P4 bar development. And that's going to let us reduce all of these costs even more, right? And in particular, the next thing we tackled was root causing, because that still required a lot of our manual effort. And why was that? Because historically, this is pretty much what the output of our tool looked like. I previously told you, just said, okay, actually it says, here was our expectation. We have some data plane packet that's supposed to get forwarded. Actually, the packet got dropped. This is the input. This is the expected output. We opened a bug. We sent them that information, and we said, tell us what's wrong with your switch, please. It turned out that they wanted more information. So we, over time, had to answer a plethora of questions. And as we went through these questions, we discovered that there were some similarities in the things that they were asking us. And rather than us going through and looking at the failures each time, we thought maybe we can actually automate collecting some of this information for them. That would be amazing, right? And here were some very common questions. One of the most important things you ask first is this a regression? Like, do I know that something that I did in the last 10 days made this fail, or is this a totally new test? That turned out to sometimes be surprisingly hard to answer in earlier iterations of this tool. Is this an outlier, or is this normal? Is this a flake? Can I reproduce this? Is it even a valid input packet for some, to everyone, unknown definition of valid? How do I specifically reproduce this? And why do we, the P4 team, expect this particular packet? I think this packet should definitely be dropped. Okay. And so right now, or initially, all of these questions required a human to answer. But there are some of these things that we clearly can make a lot better. So one simple solution that Angela pretty recently implemented to track whether this was reproducible or just a flake is, let's just send the failing packet 100 times and see how often the same thing actually happens. And that turns out to actually give you a remarkable amount of information. I even wrote down some of it that I thought was, well, I guess I didn't. And here was one interesting thing that this tells us. Was this issue caused by something like a link flap, QoS drops, or like queue fill-ups, right? Rate limits, any of these sorts of issues? We could almost immediately rule out once we did this, because it says 100% of the time this was reproduced. And if it said about 45, now we knew where to focus our efforts. They also asked us, why do we expect this? So we said, well, why don't we automatically generate the packet traces? And then we can give them what tables it should have missed, what tables it should have hit, when it should say that it's dropping, and so on and so forth. And Ali and Angela also spent a ton of effort working on this. So this has turned out to be very useful. Frankly, a lot of it was very useful for us, particularly because now we didn't need to go through and somehow try to find these. They're just immediately there. We can also output an executable proto, it turns out. So we recently wrote this code that will output a proto that you can run in some test vector, in some test file, and it will just reproduce the failure that you saw on any testbed that you run it, assuming it wasn't testbed specific. So if it doesn't, it means it was testbed specific, and that's already useful information. report some statistics, right? If 0% of test vectors pass, that's really useful information. That tells you something's gone horribly wrong. If everyone but one passes, that's also useful. If all test vectors are dropping all of their packets, that also gives you useful information. And then we have this aspirational solution that I think we're going to start working on very soon, which is well, this kind of says it all. Interpretable machine learning, right? But in the classical sense of the word machine learning. You could imagine just making a decision tree. What if we figure out what is the characteristic of the packet vector that makes it most likely to cause a failure? And then we just create a decision tree based on this, right? So for example, this can immediately tell you that every test vector that expects forwarding failed. Where should I focus my debugging efforts? In the forwarding. Packets or ports are probably down or something, right? This gives you useful information. So that's all I really want to say about this. And so in conclusion, using P4 as a specification language and having a runtime checked switch API schema that's generated from it lets us kind of tame the switch ASIC beast, if you will, giving us predictability, optionality, and improving velocity. Data plane validation as a service provides this nice power that we talked about, where we can give P4 bar, as we call our P4-based automated reasoning suite, to any user through a simple function call. And we can start automating root cause analysis instead. We're starting to have customers, and we can focus on our core competency, which is improving the infrastructure. And finally, I wanted to briefly mention some ongoing work, which is trying to open source as much of this as absolutely possible, so we can give this to external vendors, JDMs, anything like this, and this DVEST detective stuff that I was recently mentioning that didn't have a sexy name when I said it, which is this machine learning. Yes, I will happily take questions, maybe.
Right.
Yes, great. I will happily take questions.
So it's a quick question. Have you considered adding attributability? Like, who put this bogus entry in? What line of code put this bogus entry into my flow table?
So the problem is the way that it's set up now, we don't actually quite know that, right? The entries are telling us what the intent is. That's the only information we have about the intent. So our assumption, baseline, is that the entries are correct. Now, whether or not they are, we actually can't tell without a different level of testing, right? This is just going to say, does the entry even work correctly? If it works correctly, but it does something totally different than what the user wants, we'll say, amazing.
Maybe, so some important context. So we use this, we use an SDN architecture, right? So what we're testing here is the switch in isolation, separate from the control plane. So we're not testing whether control plane generates the right table entries. That's a separate problem that's also interesting, and we're also starting to work on that, but it's not solved by this too.
Then my other quick question was I liked that the first block in your system, the P4 symbolic. I wonder if there's any overlap. My question is there any overlap or connection to sort of like header space analysis? It seems like it might be related.
Yeah, so the technology that both of those tools use is symbolic execution. So very much very related. Yes, absolutely. Yes.
And the next talk will tell you very much about that.
Your P4 program is very simple, right? Relatively speaking. How well does this work with complex programs?
It depends a bit how complex is complex. When we say our program is simple, it's probably the simplest one is maybe in the order of 1,000 to 2,000 lines, and the most complicated one now is probably something like 5,000.
Also, the next talk talks about scaling this to larger programs, so you might be interested in that.
All right. Two questions, really. Do you publish your P4 program testing for the switch vendors?
Yeah, all our code is published. Actually, it's part of the Sonic repo. So if you go to Sonic pins on GitHub, you will find all our code.
Okay. The second question is to how you emulate extensions, for example, the QoS P4 extensions in your code, or do you not use the extensions here? I mean, for example, the QoS, yes.
So currently we use BMV2 and B1 model, and that's actually all we use. And does that answer the question, or? We don't support any externs beyond the ones in V1 model, and at the moment, and we don't require any. But this is because these things we model are pretty simple. So we haven't answered that question yet. We haven't run into that problem yet.
Use the mic, please.
But maybe just to add to that answer real quick, there's actually some work by I think Andy and others to describe externs in the P4 language, and that could be used by symbolic execution to interpret them in a more generic way. And in which case we would support that in our P4 symbolic tool.
Yeah, I have just a comment, as I said before. My comment is, you said it's kind of weird that I use P4 spec language, specification language. However, whoever knows about VHDL start a specification language to describe how digital circuits are working. So what you're doing actually has been done before in different ways. So it's not really weird. It's a proper way to go, actually.
Thank you. We agree.